Hi, welcome back. In this lecture, we're going to be talking about functions and sequences. Functions are a particular type of relation. They can be partial, total, injective, surjective, or a combination of these. Furthermore, sequences are a special type of functions. In this lecture, we will define the various types of functions using examples. We will also define sequences and operations on sequences. Finally, we will present examples of specifications that use functions and sequences. A function f from a set S to a set T is a set of pairs, a relation, containing pairs x and y from the Cartesian product of S with T. But it has a special property. Element x from S may only relate to one element y from T. First, let us talk about partial functions. A partial function f from S to T relates each element of S to at most one element of T. Of course, some elements of S may not be related to any element of T. Formally, a partial function f from S to T is defined as the set containing all relations from S to T such that for all x, y1, y2, such that x belongs to S, y1 belongs to T, and y2 belongs to T, then if x is mapped to y1 in F, and x is mapped to y2 in F, then y1 equals y2. For example, let's suppose we have a function called favorite color that relates people to their favorite color. We may have this partial function that maps Anna to green, Bobby to blue, David to blue. Notice that Chris is not mapped to any color. Next, we have the total functions. A total function f from S to T relates each element of S to exactly one element of T. Formally, a total function f from S to T is defined as the set containing all partial functions which have their domain equals to S. For example, our function favorite color becomes total if we also map Chris to some element in the range, let's suppose green. So we have a total function that maps Anna to green, Bob to blue, Chris to green, and Dave to blue. Notice that all elements in the domain are mapped to some element in the range. Next, we have the injective functions. An injective function f from S to T relates each element of T, the target set, to at most one element of S, the source set. They can either be partial or total. Formally, a partial injective function f from S to T is defined as the set containing all partial functions f from S to T such that for all x1, x2, and t, x1 belongs to S, and x2 belongs to S, and y belongs to t, then if x1 is mapped to y in F, and x2 is mapped to y in F, then x1 equals x2. Formally, a total injective function f from S to T is defined as the set containing all injective functions f from S to T which are also a total function from S to T. For example, our favorite color function would be a partial injective function if we had Anna mapped to red and Bob mapped to green. Notice that red and green are related to only one element, Anna and Bob respectively. And notice also that Chris and Dave that are in the source set are not mapped to any element. Next, we have the surjective functions. A surjective function f from S to T relates every element of the target set T to some element of the source set S. In other words, the image of the function f is T. They can also be either partial or total. Formally, a partial surjective function f from S to T is defined as the set containing all partial functions f from S to T which have their range equals to T. A total surjective function f from S to T is formally defined as the set containing all surjective functions f from S to t, which are also total functions from S to t. For example, our favorite color function would be a partial surjective function if we had the mapping Anna to red, Bob to green, and Chris to blue. Notice that all elements in the target set, red, green, and blue, are mapped to some element in the source set. Notice also that Dave is not mapped to any element in the target set. Finally, we have bijective functions. A bijective function is a function that's total, injective, and surjective. In other words, every element of S is mapped to exactly one element of T, the target set, and vice versa. Formally, a bijective function f from S to T is defined as the set containing all total injective functions f, which are also surjective total functions f. In our example, our favorite color function would be bijective if we had the following mapping: Anna mapped to red, Bob mapped to green, Chris mapped to blue, and Dave mapped to orange. Notice that all elements in the source set are mapped to some element in the target set. Notice also that every element in the target set is mapped by some element from the source set and just one element from the source set. We can also use lambda notation to specify functions. For example, a function square that returns the square of a given natural number can be defined as follows: square equals lambda x such that x belongs to nat, then return x squared. For example, if we do square of 3, we get 3 squared, which equals 9. Let's use as an example a machine that stores information of readers and books, like, for example, which books readers have already read, which books are readers reading, and so on. This machine has 5 operations. It registers that a given reader started to read a given copy of a book. It registers that a given reader finished to read a given copy of a book. It informs if a given reader is reading something. It also informs which book a given reader is reading. And finally, it informs if a given reader has read a given book. Let's suppose we have 5 books in our system: Don Quixote, Ulysses, The Odyssey, Hamlet, and The Divine Comedy. Let's also suppose we have 2 copies of Don Quixote, DQ1 and DQ2. We have 3 copies of Ulysses, 2 copies of Odyssey, OD1 and OD2, only 1 copy of Hamlet, and 3 copies of The Divine Comedy. Finally, let's suppose we have 3 readers: Marcel, Thierry, and Michael. Now, in our animation, let's suppose Marcel starts reading DQ1 and Thierry starts reading UL2. Now we are able to ask if Michael is reading something, and the answer will be no. If we, however, ask if Marcel is reading something, the answer is yes. And if we ask which book is Marcel reading, the answer will be Don Quixote, because DQ1 is a copy of Don Quixote. And if we also ask which book is Thierry reading, we get Ulysses, because UL2 is a copy of Ulysses. Finally, if you ask if Marcel has read Don Quixote, the answer is no, because Marcel is still reading it. Now, let us suppose that Marcel finishes reading DQ1. Now, if we ask if Marcel has read Don Quixote, the answer will finally be yes. Let us now see the formal specification of this machine, which we called reading. The machine reading has 4 sets: the set reader, the set book, the set copy, and the set response. Reader, book, and copy are all deferred sets, which means they will have to be valued later in the development. But the set response is defined as a set containing 2 values, yes and no. We also have a constant called copy of, which is defined is a total surjective function from copy to books. We have two variables, has read and reading. Has read is a relation from reader to book, which stores the information that a given reader read a given book. So it stores the information which reader read already which books. The variable reading is a partial function from reader to copy, which stores information of which reader is reading which copy. And it is an injective function. So a copy cannot be being read by two readers. And we know that if we take reading, so if we get the copy of a reader and we get the copy of that copy, which means if we get the book that the reader is reading and we make the intersection of has read, we have the empty set. That means that readers cannot be reading a book that they have already read. The two variables, has read and reading, are initialized with the empty set. And now we have the 5 operations. First, we have the operation start that says which reader started reading which book. So we get a reader, a copy of the book, and of course the book of that copy using the function copy_of cannot be a book that the reader has already read. So if we take the relational image of that reader in the variable has read, we have the set of books that the reader has read. And the copy, or in the book of that copy, cannot be a member of that set, which means that the book that the copy is of cannot be a book that the reader has already read. Finally, we have that the reader is not in the domain of reading. That means that the reader is not reading any book, and that the copy is not in the range of reading, which means that copy is not being read by any reader. And then, if all those conditions hold, we can simply add the pair RR mapped to CC in the reading variable. When the reader finishes reading the book, we invoke the function finished. We give the reader and the copy of the book, and the reader must be reading a book, so it must be a member of the domain of reading, and that the copy is really a copy of the book that the reader is reading. So the reading of the reader equals the copy that was given to the function. In that sense, when all these conditions hold, we have that we add to has read the mapping of the reader to the book of that copy using the constant copy_of, and we remove the mapping RR to that copy from reading using the domain anti-restriction. Finally, we have 3 query operations. The first query operation says if a reader is reading something or not. So we get a reader, and if that reader is in the domain of reading, that means that it's reading something, so we answer yes. Otherwise, we answer no. The next query operation returns the book that the reader is reading. So we get a reader, and of course that reader must be reading something, so it must belong to the domain of reading. And then we return the book that the reader is reading. And for that, we first get the copy that the reader is reading using the function reading, which gets a reader and returns a copy. And then we get the copy of that book using the constant copy_of. So we return the copy of the reading of RR. Finally, we have a function that returns yes if the reader has read the given book. So we get the reader and the book, and if the given book is in the relational image of has read on the set RR that contains RR, the reader, we answer yes. Otherwise, we answer no. As we can see in Atelier B, the whole machine is consistent with, so that means that all definitions and properties are consistent among each other. Finally, let's animate this machine using ProB. And for that, we use a trick in ProB. We will define a machine, call it reading for ProB, that extends our reading machine. And all we do here in this machine is to define the constants of the readers, the constants of the book, the constants of the copies, and then we have a way of expressing who the set reader is: Marcel, Thierry, and Michael. We have 5 books: Don Quixote, Ulysses, The Odyssey, Hamlet, and The Divine Comedy. And we have 11 copies. As we said, Don Quixote has 2 copies, Ulysses has 3 copies, The Odyssey 2 copies, Hamlet 1 copy, and The Divine Comedy 3 copies. So that's only a trick to animate the reading machine using values for the sets and constants as we like. After initialize the machine, we can, as we did in our animation, say that, for example, Marcel started reading a copy of Don Quixote, the copy 1, and that Thierry started reading the second copy of Ulysses. We can see here that it's not shown here, so actually what we can do is to execute an operation, and we say we started reading, and the reader will be Thierry, and the copy will be UL02. We execute that function, and we see that really Marcel is reading DK01 and Thierry is reading UL02. Now, if we ask if Michael is reading something, the answer will be no. And if we ask if Marcel is reading something, the answer will be yes. Now, if we ask which book is Marcel reading, the answer will be Don Quixote. And if we ask which book Thierry is reading, the answer will be Ulysses. Finally, we can ask if Marcel has read Don Quixote. So if we ask if Marcel has read Don Quixote, the answer will be no, because Marcel did not finish to read the book yet. So let's do that. Let's say that Marcel finished reading the copy of Don Quixote, and now, as we can see, if we ask if Marcel has read Don Quixote, the answer will be yes. And that finishes this example. Let's now continue with our lecture. Let us now move to the second part of this lecture, in which we will present a special type of function, the sequences. They are used to describe lists of a given type, and they can be defined by listing their comma-separated elements between square brackets. For instance, we can have a sequence named colors with 3 elements in it: red, green, and blue. These sequences can also be empty, with no elements in it. For instance, we have the following sequence S, defined as the empty sequence. Furthermore, sequences may have repeated elements. For example, S can be defined as the sequence containing the elements A, B, and A. Some operations on sequences are: size of S returns the size of a sequence S. For instance, in our example, the size of the sequence colors equals 3. Another operation is the sequence concatenation. It receives 2 sequences and returns one sequence resulting from putting together the two original sequences. For instance, our sequence colors is the result of concatenating the sequence containing the element red with the sequence containing the elements green and blue. The reverse function returns the reverse of a given sequence S. For instance, the reverse of our sequence colors is the sequence containing the elements blue, green, and red. Next, we can prefix an element E onto the front of a sequence S as follows. This function returns a sequence whose first element is E and the rest of the sequence is S. For instance, our sequence colors is the result of prefixing the sequence green and blue with the element red. The function first of S returns the first element of a non-empty sequence S. For instance, the result of applying the function first to our sequence colors returns the element red. On the other hand, the function last of S returns the last element of a non-empty sequence S. For instance, the application of last to our sequence colors returns the element blue. The function front of S returns the initial part of S, that is, all elements but the last. For instance, the front of our sequence colors is the sequence red and green. Next, we have the sequence truncation. This function returns the first n elements of S. For instance, if we get colors and we get the first two elements, we have the sequence red and green. On the other hand, the sequence removal removes the first n elements of S. For instance, if we remove the two first elements of colors, we get the sequence blue. Given a set S, the set of all sequences of type S is given by the following formula. Sec of S is defined as a distributed union of all total functions from the range 1 to n to the set S. Therefore, sequences are total functions from index to elements of S. Our example, the sequence colors, which contain the elements red, green, blue, is also the total function that maps 1 to red, 2 to green, and 3 to blue. There are three special types of sequence. We have sec1 of S, which is the set containing all non-empty sequences containing elements of S. We have isec of S, which is the injective sequences containing elements of S. That means sequences with no repetition. And finally, we have perm of S, which contains all the permutations of S. Let's suppose we have the set RGB that contains three elements, the colors red, green, and blue. If S is a member of sec1 of RGB, it cannot be this empty sequence, but can be any sequence that's simply non-empty. For example, it can be the sequence containing red, the sequence containing red and red, the sequence containing red and green. It can be our example, the sequence colors that contains red, green, blue. It can be the sequence green, can be the sequence green, blue, and so on. Now, if S is a member of isec of RGB, it can be any sequence that has no repetition. Therefore, it cannot be the sequence red and red, but it can be the empty sequence, the sequence containing red, the sequence containing red and green, our sequence example, the sequence colors containing red, green, and blue, the sequence containing green, the sequence containing green and blue, and so on. Finally, if S is a member of perm of RGB, it can be any sequence that has the three colors with no repetition. Like, for example, our sequence colors that contains red, green, blue. But it can also be the sequence red, blue, and green, the sequence green, red, and blue, the sequence green, blue, and red, the sequence blue, red, and green, and the sequence blue, green, and red. Let us now present an example of a machine that registers the order of arrival in a car race. It has four operations. First, it registers that a car has arrived. It can also inform the classification of a given car. It can disqualify a car, and finally, it returns the podium information. Let's suppose the following situation in which we have a race that starts with 5 cars. And let's suppose that first the Ferrari arrives, and then the Mercedes, the Lotus arrives at third, then we have the Williams arriving, and finally the McLaren arrives. If we ask what's the classification of the Williams, we get fourth as an answer. And if we ask what's the podium formation, we get Ferrari, Mercedes, and Lotus. Now, let's suppose the Lotus has been disqualified. If we ask what's the classification of the Williams, we get third as an answer. If we ask what's the podium formation, we get Ferrari, Mercedes, and Williams. Okay, let us now see the formal definition of the machine results. The machine results has a set called car and a variable, only one variable, called finished, which is an injective sequence of cars. That means that finish is a sequence that cannot have repeated cars. We start that variable in the initialization with the empty sequence. And we have 4 operations. The first operation registers that a car has finished the race. So we get a car, RR, which has not finished yet, so it's not in the range of this sequence. As we know, sequences are total functions, so the range of the sequence has the elements of the sequence. So RR is not a member of that sequence, meaning that he did not finish yet the race. And we put that car, RR, in the tail of finished. Now we can query which car is in a given place. So we get a place, a natural number greater than 0, which has to be less or equal than the size of the sequence, the size of finish. And we simply return in RR the application of the function finish to PP. We return finish of PP of the given number. We can disqualify a car in a given place. So we receive the natural number greater than 0 of the position of the car that we want to disqualify. But before going into this definition, let's see what happens in this operation. So let's suppose we have the following situation in which the Ferrari arrived first, and then we have the Mercedes, the Lotus, the Williams, and the McLaren. And let's suppose we want to disqualify the third car, the Lotus. So that's the car in the position 3. Notice that if we take the first 3 minus 1 cars, we get the Ferrari and the Mercedes. And if we remove the 3 first cars, we have the Williams and the McLaren. So all you want to do now to have the final result is to concatenate these sequences, and then we have the sequence with 4 positions: Ferrari, Mercedes, Williams, and McLaren. And the car in the third place, the Lotus, was removed, therefore disqualified. So our operations now becomes quite simple to specify. We get a place which is less or equal to the size of finish, and then we return the result of concatenating 2 sequences. First, the sequence that with the PP minus 1 elements. So we have here the sequence with the PP minus 1 first elements, and then we concatenate this sequence with the sequence that results from removing the PP first elements. Finally, we have the operation medals, which can only be invoked if we do have a podium already. So the size of finish has to be greater or equal than 3. And then we returned the first 3 elements of the sequence finish. As we can see, in this case, not all proof obligations were automatically discharged by Probe. Even if we use the first 3 of Atelier B, we still have proof obligations that have not been discharged. Proof obligations is a subject of another lecture in this course, and we'll deal with these proof obligations later on. So let us now animate this machine in Pro-B, and here we are using the same trick we did for the reading machine. So we are extending the results machine, the one we have just seen, and we are defining 5 constants for the cars: Ferrari, Mercedes, Williams, McLaren, and Lotus. And we're saying that our set of cars, it contains all these constants: Ferrari, Mercedes, Williams, McLaren, and Lotus. So let's start this machine, and let's say that the Ferrari arrived first, then the Mercedes arrived, then the Lotus, the Williams, and the McLaren. Now, if we ask the classification of the Williams, we can see that we have the fourth place. So the fourth is Williams. If we ask the podium formation, we can see that we have the Ferrari, Mercedes, and Lotus. Now, we can disqualify the Lotus, and the Lotus is the car in the 3rd position. So let's disqualify it. And as you can see here in the left, we have changed the list of finish, and the Lotus is no longer in this sequence. Now, the Williams is actually in the 3rd position. So if we query who is in the 3rd position, we have Williams. Finally, we have that the podium formation has also changed. We have the Ferrari, the Mercedes, and we no longer have the Lotus in the 3rd place, but Williams. And that finishes the animation of our example of the car race. And that's all for this lecture. See you in the next one. Bye.